Hello, this is Noson Yanofsky. The class is Discrete Structures. We're doing sections 5.1. Chapter 5 is all about probability and counting and things like that. So it's a prerequisite. A lot of it you might have seen in high school. You will use it in probability and statistics, but more important, we're computer scientists. We're going to see a lot of data science, or you're going to see a lot of data science in your career. You're going to need to know a lot of probability. So this is an introduction to probability. It's simple, but it's very important. One other thing, this section, actually all the sections, are done very simple. They give 2 or 3 rules, and everything is derived from those 2 or 3 rules. So it's not hard, and you can figure it out. Okay, great. So we start with section 5.1. It's called Basic Counting Techniques. Or however you spell it. Okay, so the 2 rules, one is called the union rule, and again, it's so simple, it's hard to believe that it's supposed to be said. So it goes as follows: let S and T be finite sets, okay, and you want to count how many elements are in S and T. So we have 3 parts to the rule. If S and T are disjoint, okay, just to make a picture of this is S, this is T, that's not disjoint, that's not disjoint. So disjoint means here's S, here's T, their intersection is empty, disjoint. Okay, so if S and T are disjoint, okay, then the number of elements in S union T is equal to number of elements in S union number of elements in T. Can't get more simple than that. How many elements are in here or here? Number in here plus number in here. Simple as that. In general, okay, okay, number of elements in S union T is equal to number of elements in S plus number of elements in T. Okay, hold on. But here, there might be an overlap. In other words, the intersection might not be empty. Well, in that case, look what we did. We counted the number of elements in S. We counted the number of elements in T. But we have an overlap. We counted this twice. So you better uncount it. So minus S intersect T. So again, you counted this once, which means you counted the intersection once, plus twice, you counted the intersection twice. You shouldn't have counted the intersection twice, so you subtract 1. Okay? Okay, let me just give you a quick example of this. We have this class, so we have the number of sophomores in this class, and then we have the number of female in this class, as opposed to male. So the number of sophomore or female, okay, is equal to the number of sophomore plus the number of females. Well, 1 second. There are some female sophomores who I counted here and here, so you better take it out. So that's the number of sophomores intersect females, minus that. Okay, so that's pretty good. Next, so these are 2 rules. Make sure you copy them right. Let me make sure the camera's getting everything. Camera's getting everything. Okay. The 3rd rule is similar. It's 3. If S is a subset of T, then T slash S, that's minus, that means take the elements in T minus the elements in S, is equal to number of elements in T minus number of elements in S. Okay, we need a picture. Here's T, here's S. If I want to know how many elements are in here, I take all the number of elements in T, subtract the number not in it, and I get that. Okay? Okay, now, just want to do, okay, so fine, that's the 3 rules, that's it. That's one rule, okay, it has 3 parts to it, okay? But now I want to go another thing. Another consequence of the first rule, and it goes as follows, of the first part of the rule, if S1, S2, S3, we have a bunch of different sets, okay, and they are pairwise disjoint. Let me explain to you what that means. That means if I is not equal to J, this implies that SI is not, intersect. We want, not that they're different sets, but they're a pairwise disjoint. That means SI intersect SJ. Not just 2 sets are disjoint. That's what we said is equal to the empty set. Okay, so that's what pairwise disjoint means. So if you have a bunch of sets that are pairwise disjoint, you can think of these sets as like this. Okay, no overlap at all. Then S1 union S2 union S3 union union SK. How many elements are in all of them? World's simplest example. This is equal to S1 plus S2 plus S3 plus plus SK. Just to add up each individually. So, for example, New Yorkers, Union New Jerseyers, Union Californians, is equal to, and again, New Yorkers aren't New Jerseyans, New Jerseyans are in California, so these are pairwise disjoint. They have different personalities, they're different people, it's not, never the two shall meet, they shouldn't get married, etc., etc. So it's equal to the number of New Yorkers plus number of New Jerseyers plus number of Californians, etc. Okay, so world's simplest rules can't get any simpler than this. Okay? Now, let me just tell you, we're going to have one more rule called the product rule. So we have the union rule and the product rule. But I just want to tell you what this entire lecture is going to be. The entire lecture is just doing problems with these rules. And you see how all these rules, they're going to become second nature. Just want to tell you, mostly we're going to do even number problems. I'm sorry, the book does problems. You're going to read the book's problems on your own. We're going to do even number problems. I'm going to assign for homework the odd number problems, and I'm going to make a video of all the odd number problems, the answers to the odd number problems. So together, well, I'm not going to do the book's examples, although the first thing I do is the book example. Together we're going to see all the examples in the book. I strongly, strongly recommend that you try to do them on your own first, and press pause a lot while watching this video. Okay? Great. Because you have to get a feel for this stuff at your fingertips, not in your brains. Your brains, because the rules is very simple in the brains, but you have to get it, and the only way you get that feeling is to do lots of examples. Okay, so this is actually a book, an example from the book, but it's a very pretty example, and so I couldn't resist. Okay, so this is an example from page 265, and it goes as follows. Okay, so you have a set A, and the set A equals 1, 2, 3, 4, all the way to 1,000. Okay, we're going to do every part of this. Okay, so first part, question. How many integers in A are divisible by 3? Okay, so let's start counting. Okay, 3 is divisible by 3, 6, 9, 12, 15, 18, every third. Okay, and the answer is, okay, 3, 6, 9, 12, okay, 999. Okay, so it's basically every third. Okay, and the answer is 1,000. There are 1,000 elements in this set, divided by 3, but 1,000 elements is 333.333333, but obviously you don't want the 0.33. I'm asking you for a whole number answer, and so it's the floor of that, and so this is equal to 333. Great. Next, second question. How many are not divisible by 3? Question mark. Okay, so that's part of that rule where we had this picture. In other words, you have A, you have divisible by 3, okay, and we said that, okay, so if there are 333 divisible by 3, how many are not divisible by 3? So that's again out here. So it's basically 1,000 minus 333, which is equal to 667. Great. Next, 3. How many are divisible by 3 or divisible? I'm being a little bit careful with my English. I would have said divisible by 3 or 5, but I want to be explicit. Divisible by 3 or divisible by 5? Question mark. Okay, and so the answer is divisible by 3 union divisible by 5 equals, try to do this on your own. Press stop, try to do it on your own. Okay, start over. You get div 3. Let's just follow the general rule of the union rule, plus div 5, those divisible by 5. But 1 second. We didn't talk about, what about the numbers that are divisible by both 3 and 5? What do you call a number that's both divisible by 3 and divisible by 5? In other words, 3 goes in it, and 5 definitely, and 5 goes in it. Okay, so that's equal to divisible by 3 intersect divisible by 5. I want to rewrite this set as divisible by 15. Because if you're divisible by 3 and you're divisible by 5, you're divisible by 15. Okay, and now we just plug in the numbers. This is going to be 333 plus divisible by 5 is 5, 10, 15, 20, 25, 30, etc., etc. Every fifth, so we do the same trick as we did here, and you get 1,000 divided by 5 is 200 numbers. And divisible by 15, well, you do this. This is 1,000 divided by 15, floor, is equal to 66. Okay, so this is equal minus 66, and that's equal to, so plus minus, so that's equal to 467. Okay, so here we used all those little rules. Again, the rules are totally as obvious, but you have to write them down and get through them. Okay? Nice. Very nice problem. I told you it was too nice not to do. Again, I don't think I do any of the other problems that the book does, but this was just interesting and clear and doable. Next, the next thing is called the product rule. Okay, and you can see we're going to have sum and product, so that's what it goes. And basically, it goes as follows. Okay, you have to remember what the Cartesian product of a set is. Cartesian product of a set, we did that in section 1.3 in the beginning. We talked about the cross product of sets. You have a set, and you have another set, and you have pairs of elements of the set. And then at the end of that section, we talked about n tuples of sets, where you have n sets, and you have an element from here, and an element from here, and an element from here. Okay? And it goes as follows. Here's the English. It goes as follows. I'm sorry, here's the symbols. S1 cross S2 cross S3 cross Sn. Okay? You have a bunch of sets. You want n tuples of those sets. Okay? Now this consists of little numbers. We'll call them S1, S2, S3, Sn. Okay? Where each one of these belong to that set. So those are n tuples of sets. Okay, we'll see an example in a second. Well, how many elements is that? That's equal to the number of elements in S1 times the number of elements in S2 times the number of elements in S3 times ... times the number of elements in Sn. Okay, now, book makes a nice English sentence out of this, and I want to go through the English sentence. Okay, it goes as follows. If there are n1 ways of choosing a member of, oh shoot, I want to make this a K. I want to make this a K. Of S1. And stress the word "and" here. Okay? With the union rule, we were dealing with things in this set or in this set. Keyword there, or, union. Okay? Here we're dealing with the word "and." Things in this set and there are n2 ways of choosing a member of S2, and there are n3 ways of choosing a member of S3, and I know this is not correct English to put in all the n's, too bad, okay, ... there are n to the k ways of choosing a member of S to the k. Okay. Okay. So again, the way to think of this is n1, this is n2. How many elements are in S1? n1. How many elements in S2? n2. How many elements in S3? n3. How many elements in Sk? nk. Then, okay, then, I'm sorry, you're running out of space, but that's okay, because you know what's going to be there. Then, okay, I'm going to erase this. Okay, I'm going to the top. There are, by the way, you can copy this from the book, n1 times, n2 times, n3 times, n4 times, times nk ways of doing all of them. Okay, that's good. So if there are n ways of n1 ways of choosing a member of S1, and there are n2 ways of choosing a member of S2, and there are nk ways of choosing a member of SK, then there are n1 times n2 times n3 times n4 times nk ways of doing all of them. In other words, doing all the choices. Okay? Main point, the word and is going to correspond to multiplication. The word or is going to correspond to plus. Okay, we're going to see that over and over and over again. Okay, let me do a quick humorous example. Okay, if you have shirts, okay, pants, socks, okay, this is what I call an outfit for men, shirts, whatever, I'm not getting into gender identity, shirts, pants, and socks, okay, this is what I call an outfit, okay, and if you have 5 shirts and 6 pair of pants and 10 pairs of socks, okay, then question, how many outfits do you have? Okay, and the idea is as follows. If I have 5 choices for a pair of pants, for shirts, 6 pair of pants, 6 choices to choose one of these, 10 choices to choose one of my socks, okay, then I have 5 times 10 is 30 times 10 is 300 outfits. 300 outfits. Okay. The reason why it's humorous is because, as you can tell, I don't care much about things matching. Okay. Okay, but obviously most people do, so they have less outfits because of that, because they don't use the full product rule in all of its glory. Let's just make sure we understand this. The word or, and just to reiterate what I just said, and the word and, 2 different things. The word or is going to be about S1 union S2 union S3 S3 union SK. The word and is about S1 times S2 times S3 times SK. Okay. This is about multiplication. This is about addition. Okay? Those are the only 2 rules we will use pretty much not only for the rest of this section, but for the rest of the chapter. Because the rest, section 5.2 is about, you ready? Probability. Probability is just 2 counting problems. You count the number of things on top divided by the number of things that could happen. Okay? And basically, counting is one of these 2 things. That's it. Great. Okay, so now we just do example after example after example of these 2 things. Let's go. Okay. Okay, so let's do an example. Okay. Sigma is equal to A, B, C, D, E, F, G. Okay. And so we could talk about sigma squared. Sigma squared, just to remind you, is sigma cross sigma, which is 2-letter words. So this is an alphabet, 2-letter words. Okay? And we know, so we ask how many 2-letter words there are. This is just another way of writing that. So this is equal to, using the product rule, the number of elements in sigma times the number of elements in sigma, which is equal to 7 times 7, which is equal to 49. Can't be more simple than that. Okay? If I ask you how many 5-letter words there are, okay, so let's just go through this. 5 letters means you're choosing a letter for the first letter, letter for the second, a letter for the third, a letter for the fourth, a letter for the fifth. Okay, so this is equal to 7 to the 5th, okay, which is equal to 16807. Okay? I like to do these problems as follows. I like to think of a 5-letter word as I have 5 choices to make. Remember, the product rule is about making choices. How many choices can I put in here? 7. How many choices can I put in here? 7. 7, 7, 7. Okay, 7 times 7 times 7 times 7 is 1607. Great. Next, non-repeating letters. I'm sorry. Of length 5. How many words are there with non-repeating letters? And it means don't use the same letters more than one. Don't use the same letters more than once. Okay? And the answer is as follows. Again, you have 5 dashes because you have 5. You have 7 possibilities for the first, but you can't use the same letter here. So you have 6 possibilities for the second. You have 5 possibilities for the third. You have that. Okay? And that's equal to 2520. Sounds good. Okay. Okay. We're going to see a quick way of writing these things in a few minutes. Let's go on. Okay. Let's go on. Another example. You have a set S. I think this is actually a homework example, but I do it here. Okay, S is equal to the set little s1, little s1, little s2, little s3, all the way till little sm. Okay, T is equal to little t1, little t2, little tn. Okay, and now we can ask the following question. How many functions are there from S to T? Okay. How many functions from S to T? I'm going to write this a few different ways. So we can write this as the set of functions from S to T. Okay, I'm going to write it another way. I'm also going to write it as, okay, never mind, I'm going to do that later. Okay, so great. So you have to ask yourself the following question. F of S1. I want to describe all these functions. Okay, I want to describe all these functions. So Fs, a function is going to take some guy in here to here. I'm going to take this guy in here. So F is going to choose some guy in T. How many choices are there for a guy in T? Okay, there are n choices for that. Okay, little s1 could be any one of these n things. There are n choices. This is what we're talking about, choices. Little f s2 is also in T. There are n choices for that. Little f of sm also has n choices. Okay, we're describing this as a product rule. Okay, great. So, how many ways are there of making all these choices? And again, every time you make such a choice, you are essentially describing a function. What's a function? It assigns to every one of these guys one of these guys. So if you want to describe all the things that go from here to here, so you have to make all these choices. So, conclusion, there are n times n times n times n choices. Okay, how many did you have here? You had, this is n to the m. There are n to the m choices. Okay, Okay, I wanted to write this another way. I'm going to write this set as t, s to the t. You'll see why in a second. This is the set of functions from s to t. So now we can ask functions from s to t. How many are there? Answer, this is equal to, let's leave this blank for a second, what we just saw. There are the number of elements in T to the number of elements in S. This is how many choices you have for each one of them. This is how many times you're making those choices. Okay? And so you get this. So this is m to the n. I'm sorry, n to the m. Okay? Now we understand why I use this notation, because this is t to the s. Okay? T to the s, number of, okay? Now this looks very pretty. This is very nice. Okay, so that's why we use this notation, because the number of elements in t to the s is equal to the number of elements in t to the number of elements in s. So that's very nice. Great. Next, this is fine for functions, but now I want to make it much more interesting. Okay, and so I need creative erasing and creative writing. Hold on. Blue pen. Ready? Good. I have two sets, S and T. I want to know how many one-to-one functions there are. Not regular functions, but one-to-one functions from S to T. Okay? So I'm not going to call this this. Well, great. So let's go through it. This guy, you could choose any one of these. So he has n choices. This guy, we want one-to-one functions. That means two things, two different s's should go to two different t's. That's what one-to-one, no two things go to the same place. So I don't have n choices here. I have n minus 1 choices there. Okay? And for f of s of 3 member of t, I have n minus 2 choices. Okay? And for s sub n, the last one, I can't choose the same thing he chose. I can't choose the same thing he chose. I can't choose the same thing he chose. I have n minus m. I think there's a plus 1 over there. Minus 1 choices. Okay, because I did m minus 1 choices for these guys, so I have this many choices left. Choices. Okay, now I can ask how many choices do I have. Again, we're down dealing with one-to-one functions. Okay, and the answer is n times n minus 1 times n minus 2 times n minus 3. Okay, dot 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 times n minus m minus 1. Okay, that's how many choices I have. Okay, okay, now this looks very familiar because this looks like the beginning of factorial. So I'd like to write this another way, which uses this factorial, which uses the fact that we're using factorial very nicely. Okay, and we're going to go do that. Okay, so another way to write this is as follows. This is n factorial divided by n minus m factorial. Okay, so let's just make sure this is right. This is n times n minus 1 times n minus 2 times n minus 3 times all the way down to 3 times 2 times 1. And this is divided by n minus m times n minus m minus 1 times n minus m minus 2 all the way down to 3 times 2 times 1. Anyways, turns out that if you cancel this, this bottom part goes out with this whole thing, and you're left with exactly this thing. Okay, so basically, if you want to do like a stunted factorial from here till all there, but not the whole thing, you divide n factorial divided by all the factorials less than this, and that's going to cancel out the factorials. So you get that right. We have a notation for this. We call this p of n comma n. Okay, and we follow that. Oh, I'm sorry. Right. Okay. Or fine. We're going to do the notation a little different with the r. I just want to follow the book, but we're going to do that. Okay. So let's get this straight. So again, let's just go through this. We want to have 2 sets, this and this set. We're assuming this set is larger than this set, because otherwise you couldn't have, if this set was smaller than this set, you couldn't have a one-to-one function from here to here, because there's not enough elements for it to go to. Each one has to pick out one thing, but if there's less elements here than there, you can't do that. Okay, so now let's just do some notation, and we're going to use this for the rest of this section. Okay, they use a different, the book uses a different thing. P for the word permutation, because you're permuting, you're having different things. We're going to use the word permutation. P of n comma r, r is equal to n factorial divided by n minus r factorial. So that's this stunted factorial. It's the factorial, but you knock out the bottom part of the factorial. Okay? Now, again, you people have seen this in high school. So in high school, sometimes it's called NPR. But we're doing it again. Okay? We're gonna do 2 examples and then fix this in a second. Okay, so let's erase this. Let's leave it. Example. Okay. Given a group of 10 people, okay, you have a group of 10, you have a club of 10 people, you want to know how many ways are there of choosing a president, a vice president, and a treasurer. Okay, so you have 10 people, and you want to choose a president of the club, a vice president of a club, and a treasurer of the club. Okay, and the answer is P of n, P of 10, you have 10 people, you want to choose 3 of them. Let me just show you why this is done. Because you want to choose 3, why it's the same thing, you want to choose 3 of them, but you don't want the president to be the same as the vice president or the same as the treasurer, so you want, it's a one-to-one function really. Okay, and the idea is you have 10 possibilities here, you have 9 possibilities, because anybody could be the president. The vice president can be anybody except for the president, and the treasurer can be any one of the 10 people except for the president and except for the vice president. So this is equal to 10 times 9 times 8, which is equal to 720. Okay, so there are 720 ways. Okay, another example, and I think I got this from the book someplace. You have 12 horses, and they're having a race, and you want to know what the winner is, the runner-up, the 3rd place, and the 4th place. Okay, so here, 12 horses, winner, runner-up, 3rd place, and 4th place. So this is P of 12, comma 4. P of 12, comma 4. Okay, and the answer is P of 12, comma 4. Why? Because you have 12 possibilities for this, 11 possibilities for this, 10 possibilities for this, 9 possibilities for this. Okay, I don't know what 12, comma 4 is. You can work it out yourself. That's 90 times 11. You can work it out yourself. I'm going to be skipping over the real numbers Okay, but on the test you have to give me real numbers. Okay, good. Okay, now in contrast to this, where I chose a president, a vice president, and a treasurer, I can ask the following question. You ready? If I have 10 people in a club, okay, 10 people in a club, and I want to choose, you ready, a 3-member committee. Not a president, a vice president, and a treasurer, but a 3-member committee where I don't care, I don't have a hierarchy, I don't care who's chosen which. And choosing the first, the president, and the vice president, it doesn't matter how you choose them. I want that to be considered irrelevant. In other words, the order is irrelevant. Okay? So, let's say I have, let me just do this a little bit more carefully. So, 3-member committee. Okay, I have a 3-member committee. So you might think of this set as A, B, C, D, E, F, G, H, I, J. J is 10, here's 10 people. But I want to do the following. If I choose D, F, and J, this as my 3 members, I want to consider them the same thing as F, D, and J. I want to consider them to be the same as F, J, and D. I want to consider them to be D, J, F. And DFJ I did. F, no, we did the F's. D's we did. J's. J, D, F, and J, F, D. Okay? So I want to consider all 6 of these to be the same thing. Okay? So, question, how many ways of there are doing this? And the answer is as follows. Look, you can pick 3 elements as follows, 10, 3. But I want to consider these 6 ways to be the same. So divided by 3 factorial. Okay? There's a joke my father once told me. He said if you have a bunch of sheep on a plane and you want to count how many sheep there are, it's very simple. Count how many sheep legs there are, and then divide by 4. Okay? Anyways, same thing in what? Because each sheep has 4 legs. So you divide, you consider them to be 1. So we're going to consider 10, choose 3. You're going to consider 6 of them to be the same thing. Same thing. So it goes like this. Okay, now the answer to this is, well, this is 10 factorial divided by 7 factorial divided by 3 factorial. So let's write this out. This is 10 times 9 times 8. That's the number of ways of choosing 3 things. Divided by 7 factorial. The 7 factorial is going to cancel out with that. Divided by 3 times 2. Let's just do this. 3 goes out with this. This is going to be 3. 2 goes to 4. This is going to go to 4. And so you get 3 times 4 is 12 times 10 is 120. So there are 700 and... what was that number? There are 720 ways of choosing 3 people, but we're going to consider for every one of those choices, we're going to consider 6 of those things to be the same. Okay? And so there's 120 ways of choosing a 3-member committee. Okay? Again, the point is, here we don't consider the order to be important. Okay? Again, you've seen this in high school, so I want to remind you the high school notation for this. Okay? And the high school notation is very good. We're going to use the same notation also. We do it as follows. N choose R is equal to n factorial divided by n minus r factorial. That's NPR. Okay? Okay, that's permutations, but you also divide out by the number of things you're choosing. I want to divide out by that. Okay, and it's also in high school notation called NCR. Okay, so let's do it again. You're given 12 horses. Number of ways of choosing 4 winners. Okay, so here I'm not interested in who's the first place, who's the second place, who's the third place, who's the fourth place. Here I'm just saying 4 winners. I want to consider them all to be the same, and so the answer is 12 choose 4. Okay. As opposed to that, what we did last time was P of 12 comma 4. Okay, here order is important. Here order is not important. Okay, and I just want to write this one more way. This is P(n) R divided by R factorial. So you have 4 ways of writing the same thing. Great. Now we're going to do problem 4, 6. 8 is the same as 6, so we're not going to do 8. 10, 12, and 14, and 16. So the rest of the time we just do problems from the book. Okay, good. Let me erase the board. Okay, so we're going to do some of the even number problems. Okay, so 4 gives you a set A, which consists of 1 through 10. And question, how many 4-element subsets of A are there? Okay, so you have 10 elements. You have 10 elements, and you want to choose 4 of them. So that's 10 choose 4. Again, you have to write the number, but you know how to figure out the number. I'm not going to do that. Okay. The main point is sets. You don't care which one's the first one you pick, the second one you pick, the third one. So you don't do with permutations. You're doing with collections. So combinations. So that's that. Okay. 4D is as follows. Okay, 4A and B are easy. How many 4-element subsets of A consists of 3 even and 1 odd number? 3 even and 1 odd. Okay, so that's a little bit different. So what you have to do is you have to choose. You have 10 of them. How many of them are even? 5 are even. 1, 2, 4, 6, 8, 10. So 5 are even, okay, and you want to choose 3 of them. And, keyword, and, multiplication, and you have 5 odd ones, and you want to choose 1 of those. Okay, and again, we don't care about order. Okay, great. Let's do 6. Okay, we're doing A, B, and C. 6. A certain class, okay, this is important. A certain class consists of 12 men and 16 women. 12 men, 16 women. Okay, and then we do now. How many committees means we don't care about the order. How many committees can be chosen from this class consisting of 7 people? So, question, I'm not interested in the genders. I want a committee of 7 people. And so the answer is 12 plus 16 is 28. Okay? And I want 7 of them. Okay? So that takes care of that. Next, number B. 3 men and 4 women. Okay? 3 men, so I have 12 men altogether. I want to choose 3 of them, and this is a 7 committee, so I want 7 altogether. So, and if 4 women, I have 16 women. I want to choose 4 of them. So again, how many committees consist of 3 men and 4 women? Okay, so that's the answer to that. And C, let's do C. 7 women or 7 men. Okay, so this is, how many ways are there of choosing 7 women? So there are 16 women. I want to choose 7 of them. Or, another thing, or this is the union rule, plus 12, choose 7. Okay, and again, you have to fill in what the numbers are. Okay, great. Number 8 is almost the same as number 6. Committees, 4 men, da-da-da-da. So we're skipping that. Number 10, let's do number 10C. Okay, let's erase, we need room. C. Okay, let's just read the question. P is equal to 1 through 9. P is equal to 1 through 9. And Q is equal to A, B, C, D, E. Okay, now 10C. How many license plates are there consisting of 3 letters from Q followed by 2 numbers from P? Repetition is allowed. 1, 2, 3, 4, 5. Okay. How many license plates are there consisting of 3 letters from Q? So 3 letters from Q. So 3 letters from Q. So there's 5 possibilities here. 5 possibilities here. 5 possibilities here. Repetition is allowed, so I'm not going down 5, 4, 3. Repetition is allowed, followed by 2 numbers from P. 2 numbers from P, so there are 9 possibilities here and 9 possibilities here. Okay, that's great. Next. Okay, anyways, 5 times 5 times 5 times 9 times 9, I don't know, but you can calculate it in a second. So that takes care of that. Number 12. Okay, so let's do number 12. The alphabet is A, B, C, D, E. Okay, we're going to do A, B, C. And let sigma n be words of, we saw this notation before, sigma to the k is words of length k. How many elements are there in each of the following sets? Okay. So, 12A, sigma to the k, how many elements are there? Answer, 5 to the k. Can't get more simple than that. Okay, so it's basically 5, 5, for each one of them you have 5 possibilities. Next, W member of sigma to the 3, where no letter in W is used more than once. So here we have 3-letter words, and no letter is used more than once. What does it mean no letter is used more than once? That means there's no repetition. So you're going to have 5 possibilities for the first one, 4 possibilities for the second one, 3 possibilities for the third one. So that's equal to 5 times 4 is 20, times 3 is 60. Number C. C, let's do C. How many are even? Oops, no. The letter C occurs in W exactly once. The letter C occurs in W exactly once. Okay. Okay, so great. So the idea is as follows. You have, whoops, this is sigma 4. So you have 4, choose 1. You have 4, choose 1. Okay? Now, that's where your C is going to go. Okay, so the letter C is going to go there. Now, you have, from those, so he's going to choose one of these 4 where it's going to go. Now, in that one, there's going to be a C. In the other ones, you could have anything else. Okay? So, I drew this as the one they're choosing, but it could have been this as the one they're choosing, could have been this as the one they're choosing, could have been that's the one they're choosing. Okay? So each one of these is different. Okay? And so this is equal to actually 4 times 4. 4 choose 1 is 4. So this is 4 to the, Okay, you don't allow them to choose any other letters. So this is 4 to the 1, 2, 3, 4. 4 to the 4th power. Okay, number D. The letter C occurs in W at least once. Okay, so let's see how we do that. So here you have, you have 4 choosing 1. Okay, that's where the C goes. Okay, but in the other 3 positions, you could have a C, you could have a C, and you could have a C. Now, I might be wrong here. Okay, so anyways, this is 4 times 125. Okay, we allow the extra C. I could be wrong here because it could be I'm counting some of them twice. Anyways, I'm not sure about 12D. Good, next. I think I'm right, but I could be wrong. Okay, I want to do, I'm not sure about this, so I want to do it another way. Okay, and the answer is, there are 5 to the 4 words of length 4. Okay? Okay. Now I ask the following question. I want to know how many have at least one C. So what I want to do is I want to subtract those that have no C's. Again, let's go through it. Words could have no C's, 1 C, 2 C's, 3 C's, 4 C's. 4 C's. The words are of length 4, so you have those possibilities. So I want to know how many have at least one C. So it could have 1 or 2 or 3 or 4. But here's another way of counting it. Take out those that only have no C's. Okay, then you're going to have all those that have 4. So this is going to be 5 to the 4. This is the union rule again. And we're going to subtract those that have no C's. Well, how many ways are there of getting a 4-letter word without the C's? Well, you have 4 times 4 times 4 times 4. So this is 4 to the 4th power. Okay? And that's 369. Okay? So I counted too much in this one. So this is the right answer. Great. Okay? Number 14. Okay, number 14 we're not doing because let me just read to you number 14. We did it, this is the first example we did, but in the first example we did with a set of numbers from 1 to 1,000. This is the set of numbers from 1 to 10,000. So you just have to change that thing. Okay, let me just read the questions. How many numbers of S are multiples of 3 and also multiples of 7? That's how many numbers are multiples of 21. How many members of S are multiples of 3 or of 7? Or both 3 and 7. Okay? Anyways, it's the same exact problem. Instead of there, the first example we did 3 and 5. Here we do 3 and 7. Okay? Last problem. Number 16. This is the last problem we're going to do. Okay, in how many ways can the letters of A, B, C, D, E, F be arranged so that the letters A, B are next to each other? So A, B, C, D, E, F, there are 6 of those. Be arranged so that the letters A, B are next to each other. Okay, so, okay, 1, 2, 3, 4. 5, 5, 6. Okay, so here's a way of thinking about it. Okay, where's the AB going to be? The AB could be here, they could be here, they could be here, they could be here, they could be here. 1, 2, 3, 4, 5. So there's 5 possibilities of where the AB can be. 1 second. Now the AB can be AB, 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 or it can be BA, 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 BA. In other words, for each one of these possibilities, it could be AB or it could be BA. It could be AB or it could be BA. So this times 2. Great. This is AB. Next, let's read the question again. In how many ways can the letters A, B, C, D, E, F be arranged so that the letters A, B are next to each other? What about the other 4 positions? 1, 2, 3, 4, 5, 6. 2 of the positions are going to have A, B. What about the other 4? Well, you have 4 other letters, so you're going to have 4 factorial for the other position. So if, for example, if B and A are here, then you're going to have C, D, E, or F here, C, D, whatever's here, not here. So you're going to have 4 possibilities here, 3 possibilities here, 2 possibilities here, and 1 possibility here. Okay? Anyways, that's your final answer. Let's read the question again. Let's read part B. In how many ways can the letters A, B, C, D, E, F be arranged so that the letters A and B are not next to each other? They are not next to each other. Okay? Well, answer, these are next to each other. Okay? How many ways are there of arranging them all together? 6 factorial. 6 factorial minus 5 times 2 times 4 factorial. You get that answer. Okay? The minute you see the word not, you know there's a minus in there. Okay? Let's go through that again. You see the word or, you know there's a plus. You see the word and, you see a multiplication. You see the word not, you know there's a minus in there. Okay? 16C. In how many ways can the letters A, B, C, D, E, and F be arranged so that the letters A and B are next to each other, but A and C are not? I have no idea. Okay, we can't answer all questions. Okay, so that's section 15.1. 5.1. This last question takes a little time to think about. Okay, we're going to do section 5.2. But